Okay. Slide'ı da başlatalım. Geçerli slide'dan diyelim. Welcome all. If you remember last week, we were talking about the pins of 886 microprocessor, and we have progressed a lot. As you know, there were 40 pins, and we covered almost 30 of them. And where were we? We were... Oh, okay, let me remind you a little bit. There were address buses. Address bus and data bus were multiplexed together, and in order to separate them, we needed address latch enable signal and address the external latch elements were holding or catching and latching the address information with the help of address latch enable. And then during the read or write cycle, data transmit receive memory IO signals were outputted, as you remember, and also depending on the operation, if it's a read cycle, read signal was the microprocessor put zero from pin number 32 in order to start reading operation, and during the read bus cycle, read signal is high. When the read operation is started, it will be going down to zero. If you remember from the time signal diagram I have shown you before. And the last topic, the last pins I introduced you was data transmit and receive, and also minimax. Minimum and microprocessor were microprocessor 886 is working in two modes. Either it is minimum or maximum. If it is minimum, there is only one microprocessor, so all the resources are belong to 886 microprocessor. If this input 33, pin number 33 is connected to zero, it means there are more than one processor on the board. This processor can be another microprocessor or mathematical processor or graphic processor. So depending on the processor type, if there is more than one processor on the board, this input has to be connected to zero. By this way, the 886 operates completely differently from minimum mode system, and all the resources has to be shared between the owners. The owners are the processors on the board. Now, a new concept, interrupt, non-maskable interrupt, and interrupt acknowledge. These signals are completely different from the operations of the other signals, you know, read cycle, bus cycle, and all the necessary signals. This is completely different. Interrupt, as you know, as the name indicates, it is halting or how can I describe that? Imagine that there is a process running smoothly and something happens, something urgent happened, or some conditions are met. In this case, the external device signals 886 through interrupt, stating that something important has occurred, and stop the operation, whatever you are doing, stop it and jump to or initiate interrupt routine, which is a sub-program or is completely different. For example, imagine that we have got a printer and microprocessor is controlling the printing operation, and the printer device has got a microprocessor inside, and everything is how can I say, printer is communicating with PC, getting the information that it has to print out, but somehow a paper jam occurs, because it is mechanical, and it started to grabbing the paper and rolling out, but somehow paper jam occurs, and when the paper jam occurs, a signal electronically detects that a paper jam has occurred, and then it signals the microprocessor that through the interrupt, stating that stop whatever you're doing because it is not working, because the paper is not rolling perfectly. Therefore, start a new program, and the new program will be signaling the user, stating that, for example, beeping of the printer or blinking a LED will be, the operation that the new program should be controlling the blinking of a LED or making a sound, and waiting till the paper jam has been corrected. So this can be, these examples can be expanded to many different tips, we can give different examples. For example, you can say that there is a fabric printing, the controller is controlling a fabric printer, and somehow the fabric has and we reach the end of fabric roll, and it has to be stopped somehow, otherwise the ink or the paint will be wasted, etc. So interrupt is used to halt the process, whatever is going on, and start a new process. And this has been initiated in the memory. If interrupt comes, you have to, the microprocessor has to start a new program from a certain location in the memory. And of course, when the interrupt has been received by the microprocessor, we have to, microprocessor says that, microprocessor signals out an interrupt acknowledge, int A, number, which one? The pin number 24. It signals out it signals out an information stating that, okay, the outer source, you informed me, how can I say, you have informed me that there is something wrong with the process, and I understand that, and I have, how can I say, I know that you warned me, and I'm getting this. I have noted that. So stop signaling me anymore. This has to be exemplified a little bit. Imagine that since you know that this is this is just an electronic circuit, it hasn't got any sense, and it hasn't got any intuition, etc. What it does, whenever a signal, interrupt signal is present in pin number 18, it is programmed, it is designed to jump a certain location in the memory to execute a new program. So as long as there is a signal in the interrupt input, it will be always jumping to that location over and over again. But it will never, it will jump, it will try to execute the program there, but still there is an interrupt request from 18, because we never suppressed it, or we didn't say that, okay, we will be dealing with the problem, so stop bothering me, stop signaling me. So that's what happens when it receives a signal from 18, pin number 18 from interrupt. It evaluates it, then by signaling out a signal from interrupt acknowledge, saying that, okay, I got the warning, so stop sending, stop signaling me, because I will be dealing with, if you keep continue signaling me, I will never be executing whatever is necessary. So when the outer device who is sending the interrupt request will be seizing the signal, it will not be sending interrupt request, because it knows that through the interrupt acknowledge signal, it knows that the interrupt request has been taken by the microprocessor and it will be dealt with. Okay, did you understand, or is there anything that do you want me to explain further? Herhangi bir tepki yok. Anlaşıldığını varsayıyorum o zaman arkadaşlar. The third signal I will be covering now. It is the pin number 17, non-maskable interrupt. A non-maskable interrupt is another interrupt, which is, as the name indicates, it cannot be prevented. What do I mean by saying it cannot be prevented? Even though you don't know yet, there are flags that controls the whole operations in the microprocessor. Flags are, one-bit information, and through those one-bit informations, what you do, you control stuff. Which way, for example, by using the direction flag, you can control the operation direction, the reading direction of a string, either from beginning to end or from end to beginning, in two directions. And for example, if the carry flag will be controlling whether there is a carry occurred after addition or subtraction, etc. One of them is int E flag, I flag. I flag is controlling whether we are enabling interrupt or not. Programmatically, in a software, we can control whether we allow interrupts or not. If we put a certain bit value, for example, 1, we are allowing interrupt. Otherwise, we are not allowing. So it can be controlled programmatically. If you want to do something very important and you don't want to be distracted, what you should do, you should prevent interrupts coming through the interrupt flag. However, there is another interrupt, which is pin number 17. It is called non-maskable interrupt. As the name indicates, it is not, you cannot control whether 886 should be getting this interrupt or not. It is always connected directly to the microprocessor, and definitely it will be evaluated by it cannot be controlled by the flags, but 886 will be directly operating after getting this signal. This is quite important. For example, sometimes the fan on your computer is not working. Working properly. Somehow it has been damaged. Maybe you can come across with such problem. And if the fan is not working in your computer, the microprocessor will be overheated, and overheating means damaging the microprocessor or other devices. So what it has to be done, there has to be a temperature sensor, and if the temperature exceeds to a certain level, that means it is hazardous to the PC. So all the routines, all the operations has to be halted, and the computer has to be shut down. Otherwise, the computer will be burnt out. So the temperature sensor will be connected to pin number 17 for 8086 microprocessor, and whenever the temperature reaches to a certain point that is hazardous to the computer itself, then microprocessor starts a new program that is shutting down the softwarely shutting down the all operations and shutting down the computer. So what you do, you use non-maskable interrupts for the routines that is crucial. But if the operation is not so crucial, then in this case you can use interrupt input for interrupting the usual flow. Buraya kadar anlaşılmayan bir şey var mı arkadaşlar? Daha fazla ileri gitmek çözelim, çünkü bu her sene muhakkak sorduğumuz sorulardandır. Eğer varsa bir sıkıntı, yardımcı olmaya çalışayım. Her şey yolunda görünüyor, o zaman devam edelim. The other two signals, hold and hold acknowledge. Hold and hold acknowledge is similar to interrupt and interrupt acknowledge in the sense of getting the signal and informing the outer device that I have the microprocessor has the microprocessor got the information from the outer device, and it will be dealing with, and by informing by using the hold acknowledge signal, it says that I will be dealing whatever the function is. What is the function? Hold and hold acknowledge is used when there is more than one owner, one microprocessor, maybe a direct memory access device, which wants to get the ownership of the address and data bus. What I mean is, for example, even though direct memory access device, an external device, of course, this one, although DMA, direct memory access device, DMA, even though it is not a processor, it's a device, external device, and it wants to directly access memory without the help of microprocessor. We will be talking about this in detail later on. So whenever it wants to reach memory without using microprocessor, it needs the ownership of address bus and data bus, because if both of them request from RAM to read and write operation together, then there will be it will be disastrous. Therefore, whenever the outer device, external device, wants to get the ownership of address and data bus and the control bus signals, a request, hold request, has been sent by the external device to the 8086. After seeing that an external device wants to get the ownership of the buses, microprocessor sends a hold acknowledge signal back to the external device, then gets himself to stealth mode. When I say stealth mode, if you remember, last week I talked about three state, Z state. The stealth mode makes microprocessors be invisible on the lines by taking the outputs and inputs to Z state, the high impedance state. Therefore, after sending a hold acknowledge signal, microprocessor is getting into third mode, into high impedance mode. By this way, it will mimic as if it is not connected there. By this way, the ownership of the buses passes to the outer device, external device, like direct memory access. The direct memory access device. Okay, reset and ready. Everyone knows what reset means. Reset stops everything, and if the program is running, if the microprocessor is executing some program, whenever the reset occurs, it will be finishing, it will be quitting every operation, and it starts from the very beginning. And what it does, it initializes the internal registers with the initial values, and all the operations has been discarded, and it starts from, it makes a fresh start. Ready signal, it is available at pin number 20, and whenever, I should check this one, sorry, it has to be, bir saniye arkadaşlar, şeyle karıştırdım, bir an testle karıştırdım, yanlış bir bilgi vermeyeyim diye kontrol etmek zorundayım. Bir bakayım. Reset, ready. Ready'ye bakıyorum. Ben buradaki olduğu gibi okuyayım, yanlış olmasın. There is one other control signal that is involved with the memory and input-output interface. This is the ready signal. It can be used to insert wait states into the bus cycle such that it is extended by a number of clock periods. This signal is provided by way of an external clock generator device and can be supplied by the memory or I/O subsystem to signal the 8086 when they are ready to permit the data transfer to be completed. So, if you remember, I told you that a bus cycle is not only for clock, because there may be some wait states inside. What I mean is, if you remember when I show you the signals, those signals, where are they? Those signals, one bus cycle consists of 1, 2, 3, 4 clocks. And I said that one bus cycle doesn't necessarily be 4 cycle for output operations. Maybe there may be maybe the outer device, the RAM, could be slow one, slower than the microprocessor itself. So, or something is wrong with the device. So, if it cannot present the data directly, the microprocessor has to wait till the operation has been completed. So it inserts wait state, it inserts waiting clocks inside. I mean, it has to wait there. So whenever the outer device is ready, it will be signaling ready. It will be signaling ready, and then the operation will continue. The reading or writing operation will be completed. And this is true for reading or writing, and it all depends on the outer device's speed. And the last one, ready, reset, okay. During read, let's talk about data enable. During read operations, one other control signal is data enable signal. And let me show you the diagram. If you check the last row, data enabled for input bus cycle, and for the output bus cycle, it is called data enable. It needs, I mean, we need to, how can I say, we need data-enabled signal to complete reading and writing operations. Just for, if you look at carefully, read signal and data-enabled signal are almost the same, because data-enabled signal signals out the outer devices that it is time to send the information, send the data, because this is an input. So it is safe to send data to be read by the microprocessor, signaling out 0. If the microprocessor hasn't been presented address information and didn't latch them, it will not signal out the outer device that microprocessor is ready to read the information. That's why read and data enabled signals are very similar to each other. Okay, but how can I say, this data enabled signal, while read signal has been used for only reading, and during the write operation, as you can see, write and data enabled signals are almost same. Okay, so while write signal is low in here, read signal will be 1, because there is only, you can either read or write. It can be, they cannot be done together. So data enabled signal is not exactly the same of write or read signal, but it is a combination of them. So it signals out, data enabled signals out the outer device that microprocessor is ready to read or write. So it is safe to put data in or get the data out by looking at data enabled signal. So if it is 0, everything is safe. So you can either read or write data. You can put data to data bus, or you can read data from data bus. So that data enable signals out to outer devices, that outer device is RAM in this case, signals out to outer devices that it is everything is safe for the operation, whether it is read or write, and you can put the data or get the data from the data bus. Buradaydık galiba. The last two signals, bank high enable and test signal. Okay, bank high enable. The data bus, as you know, the data bus is 16-bit long, and 8-bit is low and low bytes. Low byte, and the high bytes are from D0 till AD7 is the low bank, the lower half of data bus, and from AD8 till AD15 is the higher bank of the data bus. So we can, the banking means there are two 8 bytes in data bus. The data length is a word, and it consists of 2 bytes, higher byte and lower byte. Whenever the lower byte is ready to be sent or to be read, bank high enables signal it has been signaled out. And please don't forget that RAM is, in the old times, the RAM is 8-bit long. How can I say? Within each address, there is only 8-bit, 1 byte information has been stored. Therefore, if you want to read one word from a data bus, the RAM has to put the lower byte, then the higher byte to the data bus. After that, the 16-bit information should be brought through the data bus to the microprocessor. So it signals out the outer device to the RAM that it is ready to read or it is ready to write the higher byte of the information. Burada anlaşılmayan bir şey var mı arkadaşlar? Sanki karmaşık gibi ama ben yine Türkçe anlatacağım bunu. Oradan takip edebilirsiniz. Fakat burada kısacık söyleyeyim. 16 bitlik operasyon yapabilme şansımız var. Çünkü databasımız 16 bitlik. Bunu RAM'de 8'er bitlik şekilde yani birer byte her adreste birer byte kalacak şekilde store ettiğimizden dolayı siz adresini verdiğinizde, geçerli adresi verdiğinizde, ben bunu okuyacağım dediğinizde, şu adresteki bilgiyi okuyacağım dediğinizde, eğer oradan 16 bitlik veriyi de çekmek istiyorsanız dışarıdaki RAM'e önce birinci kısmı koymasını istediniz, sonra banka enable'ı çektiğinizde ardı sıra gelen byte'ı da alıp diğer 8 bite yerleştirerek, yani orada bir device, yani bir external device aracılığıyla tabii ki bütün bunlar olacak. RAM'in 16 bitlik veriyi bize vermesini sağlamış olacağız ve bunu okuyabileceğiz ya da 16 bitlik veriyi oluşturup RAM'e atacağız. Bu amaçla da işte bank high enable'a evet şu andan itibaren higher byte'ı koyabilirsin ya da şu andan itibaren higher byte'ı okuyabilirsin diye signal vereceğiz, işaret vereceğiz. Ve test sinyali. Test sinyalini de size aslında sıkıntı olmasın diye söylemek istiyorum. Şöyle doğrudan okuyayım. The test input is also related to external interrupt interface. Execution of a wait instruction causes 8086 to check the logic level at the test input. If logic 1 is found, the microprocessor suspends operation and goes into what is known as the idle state. The 8086 no longer executes instructions. Instead, it repeatedly checks the logic level of the test input, waiting for its transition back to logic 0. As test switches to 0, execution resumes with the next instruction in the program. So whenever a wait instruction, because there are instructions, as you know, and you started learning in the laboratory, wait is one of them. And whenever a wait instruction occurs, then programmatically you are waiting to something happens. So the wait input, where is that? Test. The test input, number 23, has been scanned. Whenever it is 1, it starts waiting. Whenever it goes to 0, then we understand that the interrupt signal, whatever the causing the interrupt, is ready. The device is ready, or whatever the process is, and then it resumes from where it started waiting. If you remember the explanation I did, you can rewind back and listen what I told you. Okay. Bir geriye gidelim. If you look at here, if you look at the pins, AD16 till AD19 and also bank high enable, plus memory IO and data transmit receive, there are signals multiplex with the original signals. These are S1, S2, S0, S0, S1, S2, 3, 4, 5, 6, 7. There are 8 S signals. S means status signals that has been used to inform the devices what is 8086 microprocessor is dealing with, and now I will be introducing you this. S1, S0, these are the Q status signals. These signals provide the status of instruction queue. Their conditions are shown in the table. If, for example, 1, 0, the queue is empty. If 0, 1, the opcode from the first byte of opcode from the queue is on the queue. If you remember, actually we haven't talked about queues yet. Let me show you from. Okay, this is the internal architecture of microprocessor, and there is an instruction queue here, and I will be introducing you a lot. But I remember saying that 8086 is revolutionary from its ancestors, sorry, because it uses an instruction queue inside, and this speeds up the operation, etc. And now S signals are used to signal out the condition of instruction queue. And of course, when I say S signals, I'm talking about QS0 and QS1. And if 0, 0, there is no operation. If 0, 1, first byte of the opcode from the queue, and 1, 0, empty the queue, and 1, 1, subsequent byte from the queue, it says. And how about S0, S1, and S2? This signals out the outer devices, what is microprocessor is dealing with. For example, 001 means now microprocessor is reading something, input output. Sorry, it is reading from input and output device. If it is 101, it is reading from memory. If it is 010, I'm talking about status signals, it is reading from input-output device. If it is 110, it is. If it is 110, it is reading from memory. If it is 00, it has received an interrupt request, and now it is acknowledging it. And if it is 011, it has been halted, as in the case of waiting states. And if it is 100, it is fetching from memory an opcode. It is trying to get the next instruction. And whenever it is 11, it is passive. And also the status signals S3 and S4 are showing that the address, the memory address, or the input-output device memory address has been obtained by using extra segment, or actually it has been operated on extra segment, stack segment, code segment, or data segment. So it is showing that where in the memory we are executing, or we are reading or writing information. Okay, it doesn't make any sense currently, but after introducing the internal structure, when you come back, you will understand what's going on here. So if you don't understand currently, don't worry. After introducing the internal structure, you will understand what extra segment means, stack segment means, etc. Now, bu arada saat kaç, ne kadar zamanımız oldu? Bir bakayım. Saat 10'a geliyor. This table is important because in the past I have almost in every midterm exam I have asked questions from these tables. I wanted you to complete the table carefully. How can I say? These tables are important, and it is important in as it is. What I mean is, if in here, for example, if it is RD, yani read bar, is responsible for read control. And when I say in the exams, I say I give this table, and of course I miss out some lines, some outputs, you know, the types, and some of the names. For example, Her neyse arkadaşlar, önce şunu bir anlatalım, sonra sınavda nasıl sorduğumuzu soralım. Bu tablolar önemli. Sizin için hani not olsun diye söylüyorum. Sınavdan buradan muhakkak bir şeyler gelir. O yüzden kaçırmayın. İyi bir not almanıza yardımcı olsun. Bu kısacık bir özet oluyor aslında, her şeyin burada olduğundan dolayı. Anyway, the microprocessor's pins has been categorized according to minimum mode signals, maximum mode signals, and common signals. I will be excluding maximum mode signals from the course because it is quite complicated, and because the complication comes from the need for using external devices in order to operate parallelly. So it is really, I mean, I have to introduce new integrated circuits, and I have to give the functionalities, and if I do so, then one term will not be sufficient to complete the course. So we need 2 terms, and since we are not electronics engineer, I will not be dealing with maximum mode. I will be just introducing the minimum mode, which is the basic operations. And therefore, I will be introducing you what is specific to minimum mode signals and what are the common signals. Minimum mode signals are specific to minimum mode of 8086, means that common signals has been used both in maximum mode and minimum mode. So they are always used, common signals are always used in minimum mode and maximum mode, but minimum modes are signals are only used in minimum mode. You cannot see these in maximum mode. So what I can do, I can give you some signals, and I can say that which of these are common signals, or which of these are minimum mode signals. So you can identify them according to their functionality, and you can say that these and these and these signals are minimum mode signals, and the rest is common signals. So as you know, even the microprocessor is in minimum mode or maximum mode, we always need address information. So AD0 till AD7 address data bus. AD8, burası yanlış yazılmış yine. Burada bir terslik var arkadaşlar. Bir saniye, bu niye böyle olmuş? Arkadaşlar o ilk satırı düzeltin lütfen. AD0 till AD15 olması lazım oranın. AD0, yani çektiğim yer, fotokopi aldığım yerde hata yapmışlar. AD0 till AD15 olacak birincisi. Şurası AD15 olacak. AD0 till AD15 is address, data bus, multiplexed together. Okay? It is, since data bus is connected to these pins, it is bidirectional. It should be, the data can flow in both directions. That's why these lines from AD0 till AD15 has to be bidirectional. Forget about this line, okay? And from A16 till A19, address bus, the remaining part of address bus, plus the status bus, the status signals. So this line is not here, not presented here, and AD7 has to be AD15, okay? And address bus, the function of A16 till A19 is the remaining part of address bus, and also the status signals, and it is output. and three-state. Three-state means if there are more than one device wants to use the external sources, then the microprocessor has to go in stealth mode, and that's why these inputs and outputs of these outputs and inputs will be in the third state, and saying that these are not connected to the lines. And of course, the common signal minimum maximum is an input. We are telling microprocessor that it is either in minimum, it will be working in either minimum or maximum mode. And another signal common, which is common, read or write operation. In maximum mode and in minimum mode, you can read, as you know. Wait on test control, ready reset, and non-maskable. We have already talked about this, and these are all input signals, and interrupt request, clock, VCC, ground. They are all input signals, and they are belong to common signal. Şurada hata var. Şu hata beni perişan etti. Niye bunu dikkat etmemişim diye çok üzüldüm şimdi. Anyway, so after correcting this mistake, the remaining part is safe and fine. What are the minimum modes? Specifically minimum mode, hold request, hold acknowledge, write control, input output memory control, data transmit receive, data enable, status line SSO, address latch enable, and interrupt acknowledge. These are the signals that has been used only in minimum mode, and their types are here. So what I do in the exam, for example, I give you data transmit receive information here, and I delete this part in a table, and delete the type. So whenever you see data transmit receive, you have to write that it is data transmit receive, and the type of the signal is output, and it is three state. And for example, I say I delete test here, and then I say wait on test control, and I delete this one. So when you see wait on test control, you know that it is test bar, not only test, but test bar, and then you say input, because you know that it is an input. So usually that is, let's say, 2 points or 3 points. Whenever you say test bar, you get 2 points. Whenever you say test only, you get none, because it is not test but test bar. It has to be test bar. So pay attention to minimum, maximum bar, read bar, or write bar, input output memory bar. So you have to be careful with the bar. If you don't write the bar, then you don't get any points, because it means that you don't know when the memory action has been. I mean, if it's a memory operation, it should be 0. It should be signaled out 0. And if you don't say that, it will be, in both cases, it is active in 1, but it is impossible, because if it is 1, it should be in input output mode. If it is 0, it should be in memory operation mode. So you have to write the bars. Definitely you have to write them. Oh, at last. Up until now, I tried to introduce you the pin diagram, pins, the functionality of the pins. Now, the internal architecture, how the microprocessor has been organized or developed. It is a block diagram. As you can see, microprocessor has got two parts: execution unit and bus interface unit. So microprocessor has two not modules, but it is consists of execution unit and bus interface unit. Nothing more than that. There is one slide that it has mistake in it. We will correct it later on. And the bus interface unit is responsible for communicating with the outside. Through the buses, microprocessor communicates with the outer devices such as RAM, hard disk, ports, keyboards, printers, etc. Everything, all the data flow in and out has been controlled by bus interface unit. Okay, and it has bus. We will be talking about it a lot, and the execution unit is responsible for arithmetic logic unit. It has arithmetic logic unit inside, and it is responsible for decoding the information, decoding the opcode, which is fetched by the bus interface unit and put into the queue, and it decodes the operation and then starts controlling the rest of the process. If it is for example, increment AL. This is a simple instruction. INC space AL, increment AL. It means increment the value of AL register by 1. Probably you learned it in the laboratory, or you will learn it soon. So this is whenever it reads the opcode for increment AL, when execution unit control system decodes the opcode, it understands that the content of AL register has to be incremented by 1. So it generates the necessary signals. The AL, the information in AL will be fed into temporary registers, and arithmetic logic unit will be adding 1 to the content of AL, and the result will be put into the internal bus, and that information will be put through AL. So the number, the value of AL register will be incremented 1. So everything inside arithmetic logic unit has been controlled by EU control system. Even though it has been shown very small here, actually it is the main part. After arithmetic logic unit, it is the main part of the execution unit. Execution unit has got registers inside. These registers are shift registers, as you know. They are capable of holding information inside, and by the help of these registers, we can operate. We can do everything, actually everything. All the software you are writing is has been achieved by only using this humble circuitry. We are storing data into general registers, and we can only operate either arithmetic operations or logic operations, and according to that, we put the through the bus interface unit, we send out the results to the outer memory or into the internal registers. So if you look at the internal structure, microprocessor is only capable of getting information from a memory unit, RAM in this case, or hard disk. It is capable of reading information, a code, which is called an opcode, and also an operand, some extra information. By bus interface unit is getting this information into the microprocessor, and inside there is a decoder. Understand by looking at the opcode, the electronic device understands that it has to initiate a certain routine to accomplish what opcode tells to microprocessor what to do. And as in the case of increment AL example, it understands that after reading increment AL opcode, it understands that it has to increase the content of AL register. So it starts an operation and getting the content of AL into the arithmetic logic unit and provides a pseudo 1 in the second input. The first input will be, where is that? The first input will be the AL register and the pseudo 1 will be here, so it will be adding up and the results will be stored in AL. If it was something not the internal register but the content of content of memory cell, it has to be incremented by increment instruction, but not the AL but a memory address. Then what will happen? Bus interface unit will be producing the necessary address to get the opcode from RAM, and the opcode will be decoded by the in the execution unit, and after decoding the opcode, microprocessor execution unit will tell bus interface unit, go and fetch the following information, because that information has to be incremented by 1. So depending on the addressing mode, we will talk about addressing mode later on. Depending on the addressing mode, my bus interface unit produces a new memory location and then goes and fetches the data, brings it inside, and execution control system feeds into the arithmetic logic unit and puts a pseudo 1 and increments the result, puts it into a data bus of internal data bus, and through the internal data bus, the result will be stored at the output, which is specified by the operand of the opcode. So it looks like as if it is complicated, but everything is, well organized. So everything you do, whatever you do with computers, it is based on taking information, decoding the operation, and those operations could be either an arithmetic operation, adding, subtracting, multiplying, dividing, or incrementing, or logic operations, and or XOR, not shifting operations. Logic operations, one of them is shifting right, shifting left, rotating, all those operations that you are familiar with digital design course. So the arithmetic logic unit is just a device, is capable of doing some simple operations. But from those simple operations, you can calculate factorials, you can calculate square roots, you can do whatever we can do with whatever we can do with computers are based on only those simple operations, basic arithmetic and basic logic operations. It looks amazing, yeah. I mean, and you think about it, it is really amazing that with simple operations you can do complex operations. So let's continue. In the bus interface, the name, bir bakayım şuraya arkadaşlar. Okay. Uzun anlatacağımız için devam edebiliriz. Bir daha saate bakayım bu arada. Arkadaşlar şöyle yapalım mı? Bir 10 dakika ara verelim. Durdurabilmemiz mümkün mü bunu? Ara verelim, devam edelim. Durdurmak için aynı yere gidip kaydı durdur mu diyeceğim. Sonra devam, pause yapma şansı yok galiba.
Yok hocam, durdurup baştan kaydı başlatmamız gerekiyor.
Tamam, öyle yapalım isterseniz. Çünkü ben cidden çok yoruldum. Saat 10:15. Yani 1 saat olmuş çünkü hiç durmadan. Bir 10 dakika kadar, 15 dakika sonra buluşalım. Geri kalan kısmını anlatmaya çalışayım. Görüşmek üzere.
Görüşürüz hocam.